up to you. The same. The result should be the same. Okay? So keep this in mind. Either one is good. Okay, normally, if we use Tm mode, and then we prefer to use these boundary conditions. On the waveguide, this is the z direction. Z direction. So on the waveguide, Ez equals 0. That means this one is 0. Parallel to the surface of the waveguide. Okay, in this direction. So that's why for Tm mode, we prefer this one. However, for Te mode, this one is 0. Transverse electric, so no disturbance. Just Hz. And Hz, remember, H perpendicular should be 0. Perpendicular component should be 0. But in this case, the perpendicular component is in transverse direction. On the surface in x direction, in y direction. So how to calculate these two terms? Here. Transverse component can be calculated from here. Right? Okay? So this notation means on the surface, the transverse component should be 0. Okay? The same as these two boundary conditions. Okay, so just keep this in mind. I use the red color to highlight these boundary conditions because many students will be confused here. Why? Sometimes we use this one, sometimes we use this one. Can we use this one here? Can we use this one here? Yes, up to you. Actually, up to you. Because you can see here, if you want to use the normal component, you can use, okay, in this case, no parallel component, because in the electric field just perpendicular to the surface. Okay, so not good, not convenient. Therefore, we use this one. Okay. What's next? Next one is give you some example. Calculate this one, rectangular waveguide, and we can write the general solution. Separation of variable, even for the transverse component. Not always, not always. But for this kind of waveguide, yes. For another waveguide, if I cut this waveguide from diagonal, cut this waveguide into here, and short in this surface. Okay, here you can check your homework assignment. We have a problem like this one. Maybe let's check chapter 8. Okay, page 19, you can see here, problem 8.5. 8.5, you have a triangular waveguide. Okay, that's a special waveguide. In general, you cannot separate them, but by properly manipulate, you can separate them. Okay. Separable is a good news. And because we can separate them for rectangular waveguide, we can rewrite into this one and this one. And that should be 0. That must be 0. If this one do not equals to 0, then this one will be 0. So obviously, this one, the coefficient should be 0. Okay, that's the coefficient. And then you can use the general solution. General solution. Okay? From the general solution, next step is use the boundary conditions. And you can determine all the coefficients. All the coefficients. Okay. Now, because of the boundary, so Kz will be, Kx, Ky will be quantized. But Kz cannot. Because the waveguide is infinitely long. So Kz cannot be quantized in this case. But you can quantize Kz. How? This is a waveguide, an infinite long. So in this case, Kz cannot be quantized. If you want to quantize Kz, just terminate this surface and this surface. Then they will be quantized. In that case, that's cavity. That's resonance cavity, or across cavity. Across the cavity. Okay? So if you want to quantize Kz, yes, we can do that. From page 60, roughly about 61 or 62. Last section of this chapter, we will talk about cavity. Okay? Everything can be quantized. How about time? Time cannot quantize, but omega can be quantized. Why? Omega can be quantized because of this one. Quantize, quantize, quantize. So omega will be quantized. If this one is not quantized, then this one won't be quantized. Okay. If we have a relation between omega and the Kz, then we have a dispersion relation. Omega Kz relation called dispersion relation. Okay. So like this case, for different mode, we have different dispersion relation. Okay? Because different mode, this one will be different. The angular frequency will be different. Depends on geometry. Okay, just imagine the lowest waveguide mode for this case is wavelength equals 2 times. Okay? So wavelength equals, this is A, this is A, so total 2A. So when lambda equals 2A, that will be the minimum wavelength. Okay, you can check here. Normally, A means width, B means height. Normally. And width is 2 times, normally, for most of the case, 2 times larger than the height. So the lowest mode will be 1. So you can, from the geometry, to determine everything. The next mode will be something like this one. Or this one. Okay. You can determine everything from the geometry. Okay, this is dispersion relation. This one is cutoff frequency, but keep this in mind. Actually, it's a cutoff angular frequency. Angular frequency. So for f, you should divide it by 2 pi. Okay? keep this in mind. People will be easily confused. Jackson, Griffiths, actually F denotes frequency. Omega is angular frequency. But angular frequency too long, so people just express angular frequency with frequency only. So be careful, be careful. When you see something differ by 2 pi, okay, remember to divide it by 2 pi. Remember to do that. For frequency or angular frequency, differ by 2 pi. Okay? Wavelength is okay, no ambiguity. But here is frequency. If the frequency is greater than the cutoff frequency, then wave can be propagated because kz will be real. However, if omega equals this one, then kz will be 0. Wave cannot propagate. And less than cutoff frequency, wave can be less than wave. Exponential decay or exponential growing. Exponential growing or exponential decay. Both coexist. Depends on the boundary condition. If the waveguide is infinitely long, so obviously just exponential decay. Okay, but if waveguide is finite length, then growing decay both coexist. Okay, you cannot easily say no exponential growing mode. That's incorrect. That depends on the geometry, depends on the size. Okay, so we have 3 conditions. That means if the operating frequency, omega is controlled by user, but controlled by you. So if you inject a signal with frequency lower than this one, then it cannot propagate. If you increase the frequency to here, yes, you can propagate. You can use here. Inside these regions, they have a simple relations. However, if you increase frequency to here, what will happen? You will excite this one, this one, this one. Actually, more than that. You will excite multiple modes. Maybe 5, maybe in this case 3, but in reality, probably you can excite 100 modes. More than 100 modes. How to control this mode? That's a big challenge. So you inject a signal into a waveguide mode. You can excite all the modes. That's a big problem. That will result in a very intriguing physics, interesting physics as mode competition. Sometimes with the medium inside, such as electrons, we say mode will generate here and then convert to here and then convert to here and then go back to here. Very complicated. Or mode can compete with each other. Sometimes you win, sometimes you win. It's very difficult to say. And in that case, you can easily observe nonlinear behavior or chaotic behavior. 大混沌，非常大的混沌。Very easy. Generate chaotic behavior very easy with high order modes. And difficult to control. Very difficult to control the mode competition. Okay, but luckily, don't worry. Mode competitions belongs to advanced course like plasma physics. Okay, so don't worry at this moment. I show you many field patterns here. Okay, let's move on to this part. Already spent 30 minutes. Oh. Okay. Now let's talk about coaxial mode. The simplest case, TEM modes of coaxial transmission line. Actually, transmission line is used for transmitting EM wave. So you have many kind of structure. If you have a chance to check your cell phone, your notebook, you can see inside a cell phone, inside a notebook, they use a different structure. They use coaxial cable, yes, but not waveguide, because that waveguide, rectangular waveguide, too bulky, too large, not good for use. So they use transmission line like coaxial waveguide, and they use microstrip or strip line. Okay, let me show you what is microstrip. Microstrip consists of two materials. Conductor 1, conductor 2. So two material. And dielectric here. Dielectric here. Okay, that's microstrip. So electric field from here to here. Something like that. Okay, so it's TEM mode. It's TEM mode, microstrip. Let me show you another one. Another one is strip line. Conductor 1, conductor 2. And we have ground. So just one conductor. And conductor 2. So you can see here, something like this. Okay, and dielectric here. That's microstrip, that's strip line. Microstrip, strip line. Okay? That's for transmission line. That's very common for IC, for printed circuit board. Very, very common. Because it's convenient to fabricate. Okay, so you will see many kind of transmission line later on. But let's focus on the simplest case, TEM mode. Actually, this is TEM mode. This one is not exactly TEM, it's quasi-TEM. Okay? This is the ideal case, TEM mode. Okay, so for TEM mode, we will go back to here. We reduce to two dimensions, transverse component. So we just consider cross-sectional view only, transverse component. And for cylindrical waveguide, coaxial waveguide, we can use rho and phi Z. So we will use rho phi Z. Rho phi Z, okay? And the inner conductor, we normally use A. Radius use A. Outer conductor, radius use B. Unlike this one, we use this one as A, this one as B. Okay, people always use this notation. Okay, so the inner conductor, radius A, outer conductor, radius B. Just give you an idea. So, we know TEM, electric field, will be here. So we are going to solve this one. And HTM is related to here. We just extract the equation we derived maybe last week. And Z equals here. Okay. Write on your lecture note. Z actually depends on materials only. So how to support the inner conductor? Inner conductor cannot support in the air, so you need some material to support the inner conductor. Here we use a material to be determined. Okay? Actually, we prefer a material called Teflon. Teflon, 铁氟龙. We prefer Teflon because Teflon dielectric epsilon is small, roughly about 2.1, and very uniform, and no frequency response, almost little frequency response, and luckily the permeability for Teflon is μ0. That's why we like Teflon. What is Teflon? Teflon is a high, excellent dielectric material and flexible. And you can coat on your, how to say that? 不粘锅. Okay. 锅子怎么讲? Pan. How to say that? Someone help. 不粘锅. If you want to cook something, you can coat Teflon, and then you don't have to worry about. Okay, so let's start from here. Equation 23. Laplace equation, 2-dimension. And we can assume, let's consider the simplest case, equals 0. So we got this one only. For this one, the solution will be easy. The problem is, can we do left? Why not? Let's just consider symmetric case. Okay. Later on, we should consider this mode. Don't worry, that's for research only. At this moment, we can simply consider as mutual symmetry, happy life. Okay? As mutual symmetry, so we just consider this case. And if you want to draw the potential, it looks like here, from inner conductor to outer conductor. Looks like here. And symmetric, as mutual symmetry. As mutual symmetry means independent of the angle. Okay? So in all of, I'm sorry, it's not symmetry. It kind of looks like an ellipse because of the projector. My slide is actually symmetric. You can check your lecture note. Lecture note is pretty good. Okay. Okay, so this one tells us the solution will be easy. Phi equals, that's second order. Actually, it's the ordinary differential equation. We still, actually, it's ordinary differential equation. Okay? After differentiate, it gives us C1 over rho. Rho cancel. So give us C1. And after this one, give us 0. So this is a very simple solution. Okay? Next step is use the boundary conditions. Okay. I do not say that which one is 0, which one is not 0, but there is a drawing here. Tell us that phi outside is 0, inside is V0. Okay? That's the boundary conditions. From these two boundary conditions, outside is 0, inside is V0. From these two boundary conditions, we can determine the coefficient C1 and C2. So that's the final result. Let's check this result. Rho equals A, it should be B0, right? Rho equals B, this one is natural log 1. Natural log 1 is 0. Okay? Correct. So you should double check your solution. Okay? And once you have potential, you can calculate electric field. And the electric field is easy. But this time, we will consider G and T. Consider everything. Because of azimuthal symmetry, so no phi dependent. Just rho, Z, and T dependence. And another case, H, the same. Rho, Z, T dependence. The ratio between E and H here, the G dependence, that's the impedance. Impedance in Chinese is 阻抗. Okay? For example, if you have RG you will see, you will have a chance to see many kind of coaxial cable. RG50, RG75, RG3, that's coaxial waveguide. RG50, 50, the ratio between Z is 50 ohm. That's the ratio between E field and H field. Okay, just 50 ohm, the same dimension as resistance, same dimension, 50 ohm. Okay, so that's the ratio between E and H. Okay, from here you will know one thing. We assume this inner is V0, outer is 0. Why? Because outer, you will have a chance to touch the outer waveguide. In order to protect yourself, you assume it's grounded. But in fact, it's not. Be careful. It's time dependent. Can be 0, can be switchable. Right? It's AC, not DC. It's AC. This one is AC. Depends on time, depends on Z. Therefore, if you have a conductor, if an outer conductor, you will have an inner conductor. Okay? You will see some potential difference. Looks like sometimes in this place is 0, but in other place, something like you will have see some minima and maxima, minima, maxima. So actually, inside the waveguide, inside the surface of the coaxial waveguide, is not equal potential. Potential depends on time, depends on position. But outside is still grounded. Don't worry. So if inside we have a 1 megawatt, maybe high power, or you have 1 gigawatt, 1 gigawatt, extremely high power. For fusion, you will have 1 gigawatt propagation inside. Electric field is very, very large inside, but outside is still safe. You can tolerate it, don't worry too much. But if the inside electric field change very fast, and potential is not equal potential inside. Outside, it should be equal potential. Okay. It's difficult to understand. Because people always think everywhere there should be equal potential for a conductor. But actually, it's not. It's not. For a rectangular waveguide, electric field may be in this direction, sometimes in this direction. Okay, so potential difference between here and here will be different. And propagate with time. Okay, so you should keep this in mind. But outside is still safe. It's still safe. Because we have a lot of free charge. Will neutralize the potential difference inside. Okay. Think about it. Okay, let's move on. Just give you some idea about the application of the waveguide mode. With how to excite a specific waveguide mode, for example, TE21. Okay, we can excite with a waveguide like this one. Okay, so it's a new idea. And excite TE21 cylindrical waveguide mode, TE01 and TE41. No one excite this mode with high conversion efficiency. We are the world record, and we have the widest bandwidth 10 years ago. Okay, how to calculate this one? We can use the idea. That's the fundamental mode, rectangular waveguide. This waveguide, and we have a small opening here. That's coupling hole. Couple the wave from here to here. How to do that? The wave from here to here, it will generate electric dipole or magnetic dipole. How to do that? Let me show you. If we have a small opening here, and we have electric field, The electric field, that's conductor, electric field. So this case looks like electric dipole. Okay. So a small opening can generate electric dipole. Another case, if you have a magnetic field here, this small opening can generate magnetic dipole. Electric dipole and magnetic dipole can be used to excite waveguide mode as a source. Dipole radiation. Okay. So it can jointly generate any mode you want in principle. So you can calculate the Poynting vector, energy density, almost everything. And you can find the ratio of the desired mode and unwanted mode. Okay, this one is for 100 gigahertz, sub-terahertz, or close to terahertz. Okay, that's the first one. And then we increase the frequency even higher to 200 gigahertz to a higher order mode, TE02 mode. Actually, it's quite small here. How to machine this one? How to fabricate this kind of structure? Actually, you cannot fabricate this kind of structure with traditional techniques like CNC, computer numerical labs. You cannot use CNC. We use LIGA, X-ray microfabrication in collaboration with Synchrotron Radiation Research Center to fabricate such a small device. Okay, 200 gigahertz, as well as 400 gigahertz and 1 terahertz. The component quite small. You cannot see with your bare eye. They're very small. And that's extremely small, extremely high frequency. But for some applications, people prefer low frequency. For example, 2.45 gigahertz plasma reaction chambers. In this case, we have two ideas. One is we use a TE3130 mode. TE03 mode. 0, we have azimuthal symmetry. So azimuthal symmetry. Okay, we can generate large area and uniform plasma. Another one is this one. We use an array, phase array, 2 by 2, and we can generate uniform plasma over 50 centimeter by 50 by 50. 50 centimeter by 50 centimeter. Remember, 30 by 30, 12 inch. This is much larger than 12 inch. Okay, much larger than the state of the art. Uniform, quite uniform. Actually, we can enlarge the uniform region to 4 by 4, and it will be 1 meter by 1 meter, and 16 by 16. There will be 4 meter by 4 meter. Extremely uniform plasma. Okay? This one can be used for amorphous silicon solar cell. Okay, for this one. Therefore, this one, we publish this paper easily. They like this idea very much. And we also use waveguide modes to process material, to heat the material, to simplify, to shorten the processing time, and improve the material's quality. We just put material here, one focus and the other focus left open, so we can put material here, and result will be quite good. Okay, that's for different material. More example. This one is not 0 because we have 1, 2, 3, 4, 5, 6, 7, 8. Actually, this is TE41 and TE02. We can use something looks like rotary joint. What is the rotary joint? That means we have these two joined together with a ball bearing and can be rotatable. Rotatable. Okay? So you can control your signal to different direction without loss. Without loss. Because this two mode is the best. This mode is the best mode. TE01 mode. So once you can excite this mode, you can minimize the transmission loss. For example, we have a waveguide here, we have another waveguide here, and this one is rotatable. Just imagine this is circular. Rotating, and you will generate some gate. Okay? Once you have a gate here, you will have some discontinuity. And discontinuity will be discontinuous for the boundary. For discontinuity, it will reflect back. Or the wave will be transmitted or leak from here. That's leakage wave. Leakage wave. Maybe 10% or 20% or even higher. Leakage wave will be very high. So properly design this kind of rotary joint, and you can design circulator, isolator, power divider, antenna. That's for rotary joint. You can design phase array antenna. So excitation of waveguide mode will have many applications. Okay, you can find your own applications. I start to study this problem roughly when I was a PhD student. I excite the fundamental mode, TE11 mode, cylindrical waveguide for the first time. And later on, I found it very interesting. And my students, for example, looks like a Y shape here, Y. Okay, so I call this kind of waveguide as Y-type mode converter. Why? Why I say it's Y-type? Y-type, because the student who invent this idea is Yu Qingfang. Okay, he is Dr. Yu is a manager of TSMC now. Please think about this idea. He proposed this idea for the first time. Dr. Yu is a Y-type mode converter. And I like the idea very much because it's simple. And you can excite something with symmetry. With symmetry, yes, we can easily excite. Okay. Any question or comments? I will stop here for a few minutes. 有建议吗？波斯线。Any idea?
直蛮好奇，就是他们在设计这些 waveguide 的时候，是真的用这种电磁学的知识去算出来再设计，还是随便弄个形状之后结果才？对，我一直有这个疑问。
说呢？
Very good
有
point.
钱人的知识，
有钱人的知识。
但是那个蛋怎么
James' question is, you know the ideal electric dipole excitation of the dipole first, or you just try first? Which one? Actually, most of the student, he know nothing about electric dipole. He has no idea how to design a suitable dipole. But I will teach him step by step, give him an idea how to excite electric dipole, how to excite magnetic dipole, how to excite the dipole moments. And from the dipole moment, you can synthesize any mode you want. Okay. Idea is simple, but for a beginner, it's not easy to understand. So for the beginner, the best way is just give him or her the software. Let him try. Let him try to copy some previous idea, try to reproduce the design first. Okay, that's good for learning process. If he or she starts from electric dipole, magnetic dipole, it will take too much time. Okay, we'll slow down. So normally, I just give them the simple idea and let it go, let him try. He can try any idea he wants. Okay. If he or she cannot find some new idea, let's go back to Yu's idea. Y-type power divider. Recently, we tried to design a very unique mode. TM11 mode. TM11 mode is very special mode. No one successfully excite TM11 mode with broad bandwidth before. No one. Because it has something very unique. Okay. So at least the student is the ED. The ED tried to, he's the second year master students. He tried to design this one and fabricate this one. Right now his design looks good, but you know, fabrication is another story. That's another story. Okay. Yes?
So can we consider the superposition of different waveguides?
Yes, we can do that. We can do that.
So how these modes are, suppose I have a coaxial waveguide and a triangular waveguide, I just attach these two things. So how the modes will change?
Mode will change a lot. Normally, for example, just give you an idea. We have a cylindrical waveguide and we have rectangular waveguide. And we try to connect these two together. What will happen? Okay, there's a discontinuity. So field will change a lot, but keep this in mind. That's the field pattern for cylindrical waveguide. That's field pattern for rectangular waveguide. Looks similar here and change. So The idea for mode conversion is taper, gradually change, not sudden change. Sudden change will have reflection, just little transmission. But if you change little by little, gradually, then you can convert this one to here. You have a chance to do that. For example, squeeze the waveguide. Squeeze the waveguide, it will look like this one.
Suppose if I covered the boundary with some kind of specific dielectric material, can I get the same mode?
You want to use different material from one material to another material.
No, so we are just concerned the same configuration, like we have a coaxial wavelet and we have a triangular wavelet. And at the boundary we are just covering with some kind of a specific dielectric material. So if you have tuned this dielectric material, can we get the same mode?
Yes, we can do that. For example, if I have two waveguide, one is rectangular waveguide, the other is also rectangular waveguide, and we have material epsilon 1, material epsilon 2. Yeah, wave can propagate, but because they have two material, so they will have some reflection. Some transmission, just like wave, just like light from one material to another material. Index of refraction, N1, N2. Same idea. Actually, later on, you can calculate. Their equation is exactly the same. Same equation as the light. Same equation. Wave phenomena were always the same, including matter wave. Matter wave, EM wave, stream wave, almost all of it, sound wave. Their basic phenomena is the same. Their basic phenomena are the same. Therefore, you can use the idea of the wave to all the case, almost all the case. Okay? Any question? It's not hurry, we still have time. 张佑轩，会冷吗？对，因为防疫的关系，我们都要让窗户打开。哦，没关系，你那个还可以。Any questions? 陈伟忠呢？没有。要不然林凯翔。许俊祥，我们有两个祥，就是许玉祥，你们两个认识吗？许俊祥、许玉祥，所以之前认识吗？哦，不是兄弟啊。OK。Okay, we still have 10 minutes. What's next? We have E field, we know how to excite the wave. Next one is calculate pointing vector, power density. Okay, so we will talk about energy flow and attenuation in waveguides. Okay, just a moment. Maybe I should tell you something. Right from the beginning. Jackson used a very interesting title here. Fields the surface of and within a good conductor. Actually, fields at the surface of a good conductor and fields within a good conductor. At the surface of a good conductor and fields within a good conductor. Okay. So, very difficult to understand for a non-English, non-native English speaker. Here is another example. TEM modes of coaxial transmission line. TEM modes of parallel wire transmission line. But here, we just consider coaxial only. We do not consider parallel wire, 两条平行线 transmission lines. Here is the same. Energy flow and attenuation. Energy flows inside a waveguide, and energy attenuation in waveguides. Okay, so we should calculate the power loss of a waveguide. We have considered, let's consider TM mode first. A TM mode, we have E transverse component, and plus this one. Because TM mode, we have EZ. H, we just transverse. So just transverse, therefore we say transverse magnetic. Okay, TM modes. And in a medium with real epsilon mu. So we can simplify the problem first. We have medium with real epsilon mu. In general, no such material. Even for Teflon, this one is very close to mu zero. This one, yes, very good. Real part, 2.1. Imaginary part, very, very small. Roughly, sometimes maybe here. That's good imaginary part. That's good assumption for this case. But keep this in mind. Teflon is a pretty good dielectric material, but even for Teflon, we still have imaginary part. Okay? So we should consider complex pointing vector here. The complex pointing theorem tells us that this one, Z dot E, and energy store and pointing vector. X, the notation is here. X equals this one. That's the definition. That's complex. If you like, you can take the real part. You should take the real part. Or you can just start with this one. Okay. If you don't understand, you have no idea about this one, you forgot everything, please go back to chapter 6. Chapter 6. Actually, we test test your understanding twice. So in principle, you should remember there is a complex pointing theorem. And we have complex pointing theorem. That's the definition. And 1/2. Just write everything down here. That's complex pointing vector. Complex pointing vector. And then what can we do here? We can simplify this calculation a lot. For TMO, we just substitute HT. HT is related to ET. Yeah, HT is related to ET. HT is related to ET, transverse component. Okay, substitute everything inside, and then you can calculate. This one gives us a simple relation. EZ cross this one. Give us this one only. That is this one. And E transverse cross EZ cross E transverse. Give us this one. Okay? And how to calculate this one? E transverse comes from here. Okay? And E transverse, okay, you can calculate from here. Okay? In the Z direction. In the Z direction. Okay. And this is a scalar. So just in the Z direction. How about this one? This is a vector, actually. Is a vector in transverse component. Okay? So we have vector here and vector here to be determined. Okay. Next step, we just care. We know the wave will propagate inside the waveguide and just in the Z direction. Just in the Z direction. So if we want to calculate the energy density, the power, we just consider the time average power in the Z direction. Just consider the Z direction. In that case, we just consider this one. Because we know waves cannot propagate in transverse direction, just in the Z direction. So for the inner product, and take the real part of this one, and integrate the cross-sectional surface. The area A denotes the cross-sectional area. That's the cross-section. That's the cross-section. This is the area. Okay? So after integration, after simple manipulation, we just consider this one. Okay? That will be much easier. And we omit these terms because it transfers in other direction. Actually, the wave inside the waveguide is doing, bounce back and forth. Bounce back and forth inside the waveguide. But wave energy cannot propagate in this direction, cannot propagate in this direction. So if we want to calculate the power flow, we just consider the Z direction only. Okay? Just consider the Z direction. And then, if we want to consider the complex pointing vector, we just calculate one term. What else? Once again, Green's first identity. Green's first identity. Remember, first identity is divergence phi gradient per psi. Divergence something equals the surface integration. Okay, that's Green's first identity. Okay, divergence something and divergence this one again become phi Laplacian per psi, and divergence this term gradient phi dot gradient per psi. And here we are very lucky. We are going to use these properties, Green's first identity. Let phi and per psi be independent of z. Okay, and apply this equation 1.34 to a slab of n surface A. Just consider a small slab, inside, outside. Let's just cut this section and cut this section. Separate a little, delta z. Separate a little, thickness, delta z, maybe small. Okay, cross-sectional A, cross-sectional A, the same. So this is volume integration. And this one, surface integration, we can simplify into dz times dl. dl is this one. And the surface integration on the two ends of the slab. Okay, I will stop here. Next time we will start from here. Okay, I will talk about power flow, energy flow. And so we will talk about energy flow, power flow for this one. And TE mode, that's for TM mode, that's for TE mode. Quite similar, TE mode. Look at the field pattern. Coefficient, quite similar, right? They have similar equations. So, and energy loss, energy in a lossless waveguide, almost no loss the waveguide. This one is still the same, and you can consider all the case. And later on, we can consider TM mode and TE mode. I summarize almost everything for you. So if you have a chance to study this case, you can open your lecture note again. You can quickly pick up the knowledge you learned here. And then I will talk about attenuation in waveguide due to omega loss. That's conductor loss on the side wall. Because the conductor, the wave can penetrate into the conductor a little bit. So omega loss will play some role here. Omega loss. So energy will propagate in this region, but waveguide will be heated. Okay. Normally, if you have 1 gigawatt here, this one will be extremely high temperature. Okay. Just give you an idea. That's conductor loss. And if you have dielectric inside, then the dielectric will burn out for high power. That's power handling capability. So, depends on the material. Okay, next time I will cover up to this page. I will show you if you excite TE01 mode, then the transmission loss will be extremely small. Extremely small. How to excite TE01 mode for terahertz waveguide? That's a big challenge. So I will show you another paper by Dr. Yao. Dr. Yao. Yao Xinyu. He invites a new terahertz waveguide for this one. Okay. That's another terahertz waveguide. Simple. But the transmission is actually quite poor. His idea looks great, but energy can transfer from here and here with loss roughly about 50%. So actually it's quite poor, but he is the first one. He is the first one. Professor Wittmann is the first one to propose this idea. Therefore, he received many honors. Many honors. Okay, so next one I will talk about up to page 60. Okay, see you next time. Let's invite our TA.
There I will give a problem 8.6 and problem 8.18. The problem 8.6 say we have a resonant cavity of copper consisting of a hollow right circular cylinder of inner radius r and length l with a flat end space. And that look like these shapes. We have two end face and with inner radius r. And the cavity have a length L. And problem A from us determine the resonant frequency and of the cavity and all type of the wave inside the cavity with this unit not clear here. And plot the lowest four resonant frequency of each type as a function of R over L for in the two, from 0 to 2, and the mode have AED, and this problem as does the same mode have the lowest frequency for all R over L. Okay, so since the TM mode cannot exist in a single hollow conductor, so we only need to consider either T mode or TM modes. And this is a boundary condition for conductors. The electric field and the N is the normal direction of the surface, and N cross E is equal to 0 at the surface, and dot B is 0 at the surface. So for the TM mode, we have the transverse electric field equal to 0 on the two end face, and Z direction field is always equal to 0 for TM modes, and the Z direction field of the Z direction electric field is equal to 0 at the cylindric surface, and final is the row direction of the B field is equal to 0 at the cylindric surface, and similar things for TM mode, but since this is a TM, same things for E mode, but since this is the T mode, so the Z direction field of the Z direction electric field is always 0 in this case. And from textbook, we know that the transverse electric field and transverse momentum field can compute from the Z component of electric field and the magnetic fields. So, and the H field is defined, and the H is defined by the Z direction across the transverse electric field divided by impedance. And gamma squared here, we define this denominator by plus a gamma squared. Okay. And in this case, the Z component field and the electric field can write into this form: A sine kz plus B sine kz times psi sy. In this psi sy is need to be solved. And from the boundary condition of this cavity, we know that at the end of this, the divergence of the transverse electric field is equal to the z component, z derivative of the EZ at the end phase. And since the transverse electric field is equal to 0 at end phase, so we know that the derivative of the z component should be 0. So we only keep the cosine terms. The sine is eliminated. And another boundary condition should give us a steady wave condition. So k is equal to the p pi times z divided by l, and p is a positive integer of 0. And after solving the z direction, the cosine is satisfied a Helmholtz equation. The Laplace operator plus gamma p here. Gamma p is the constant depending on the integer p. And since this is a cylindric cavity, so we change our coordinate into a cylindrical coordinate. And after the separation variable, we can solve the phi direction is equal to exponential I m phi. And m is the integer because the function should be single value after we change our phi to 2 pi. And after the calculation, we now need to solve the row directions. And row directions satisfy the Maxwell function equation. So after we solve this differential equation, we know that this g of rho is equal to the Maxwell function Jm times amplitude. Okay. And now, since the z component and the electric field, the z component field should satisfy the boundary condition on the surface, cylindrical surface it should be equal to 0. So g of r should equal to 0. Then we have a gamma p times r is equal to the nth root of the Jm Maxwell function. And it looks like this. This is the first root of the J0, second root for J0, and so on. And after we calculate this, after we satisfy all the boundary conditions, we can find the cutoff frequency omega m/p is equal to this. And because this is a cavity, so we need 3 integers to define the modes inside the cavity. So after the calculation, the first and the lowest 4 cutoff frequency is at least 3 points for S01, S11, S21, and S02. And after we plug these numbers into the cutoff frequencies formula, we can plot this graph. The lowest 4 frequency at the beginning is the 01 modes, and after the R of L is increased, it will be a cross here, and then the lowest 4 mode will change. Yeah. And the same thing is for the TE modes. The calculation is similar, but because this is the TE mode, so instead of calculating the electric field, we use the H fields. And again, we calculate the H fields and satisfy the boundary condition. We find that it should be assigned here. And again, we solve the Helmholtz equation in the cylindrical coordinate and find the solution should be a Maxwell function. But the difference is the boundary condition here is different. For TE mode, the boundary condition is the BZ component the derivative of the BZ component should be 0 at its surface. So instead of we need to find the root of the Maxwell function, here we need to find the root of the derivative of the Bessel functions. So we use a prime here to denote the root of the nth root of the Jm's derivatives. So after this calculation, we can define a new cut-off frequency, and the numerical value of the sixth root is S11, S21, S01, and S31. And again, we can plot this graph. At the beginning, again, omega 111 is dominant at the lowest pole frequency. And after increase the R over L, there will be a plus here. And the lowest frequency will change. The mode will change. Okay, the problem is if we use a real value, R is equal to 2 cm and L is equal to 3 centimeters, what is the numerical value of the Q factors for the lowest resonant mode? And because we have a specific R over L, so we know that for this value, the lowest mode is the TM010 modes. And so for the TM010 modes, we calculate the E field and the D field for all components. The EZ is equal to this. The BZ for TM mode is 0. And the transverse field is equal to this formula.
In this case, yes.
And after the calculations, in order to find the Q factors, we need to calculate the stored energy in the cavity. The stored energy is equal to the integration. So after we use the integration formula of the Bessel function, we will get the U is equal to this. Epsilon A was E0 times the volume times the J1 squared divided by 2. And for Ohm's type power loads, we need to find the induced current at surface and integrate. So after the integration, after the calculation, we can find that the power loads is depend on these coefficients times another geometric factors. And since the Bessel function is hard to deal with, so you need to find the formula on maybe books or the website, and you will know that for arbitrary Bessel functions integration, the integral result will be this kind of response. You need to take the limit. So after these tedious calculations, you will find that you need to use this form Bessel's equations or its recursion relations to find the integration is finally just J1 squared divided by 2. Yeah, it's the same. So after we use this formula, we can calculate the power loads, the energy stored in the cavity, and the Q factor is omega times U divided by P. So finally we will get that Q is equal to this. And we can calculate the inside the cavity because we don't assume any medium in the cavity. So the epsilon is equal to epsilon 0, mu is equal to mu 0. And the value is about this. So, and the omega TM mode and the TM mode, TM010 mode frequency is about 3.6 times 10 to the power 10. And it's just about 5.74 gigahertz. And the conductivity of the copper is 6 times 10 power 7. So the skin depth of the copper is about 860 nanometers. So the Q factor finally we will get is just 12 thousandths. Okay. And the problem 8.18 is want us to use Green theory to calculate the orthonormal relation of the both TNT or any mixed modes, satisfy the boundary conditions. So for TN modes, we have the electric field. EZ is equal to the psi times exponential IKZ, and ET is equal to the gradient psi times IK divided by gamma squared. for T modes, we have hd is equal to the exponential igt times psi, and h transverse is equal to set gradient psi times ik divided by gamma squared. So since psi satisfies the two-dimensional wave equation for both TE and TM modes, with the different boundary condition for TE and TM modes. For TM modes, psi satisfies the boundary condition. Psi is equal to the 0 value at the surface. And for TE modes, psi, the derivative of the psi is equal to 0 at the surface. So if you want to prove the orthogonal relation, we need to choose. We first choose different psi associated with different eigenvalue gamma, and they both satisfy the wave equation. And we multiply the first by psi mu, the second by psi lambda, and subtracting these two equations, we will give gamma square mu, subtract gamma lambda square is equal to some formula like the Green's identity that we can use. So after we integrating over the cross-sectional area of the waveguide and use green theory, we can find that after this calculation, the left-hand side is the gamma mu square minus gamma lambda square times the integral. The right-hand side is the loop integration. But for the TE or TM boundary conditions, we know that either this psi is equal to 0 at the surface, or the psi differentiation of the psi is equal to 0 at the surface. So the right-hand side should be 0 for both TE or TM mode. So for problem B, you want us to prove the equation 8.131 to 8.134 in the textbook. So the 131 gives the transverse electric fields in the product with different modes should be orthogonal to each other and with appropriate normalization. So to prove this, we first should consider the transverse mode can be rewritten into the z component field. But for the TE or TM modes, the formula will differ. For TM, the transverse mode of electric field is equal to gradient Ez. For the transverse electric TE mode, the transverse electric field is equal to the z direction cross the gradient h. So for two TM modes, the inner product of the transverse electric field is equal to this. And again, we use the Green's identity and the Green's theory. We can find that for the first term, it will vanish because of the TM mode boundary condition, because our E is proportional to the psi. So we only have the second term, and the second term have a Laplace Ez here, but since the Ez satisfies the wave equation, so we can change and replace the Laplace Ez to gamma lambda square. So, and after this calculation, we can find that the transverse fields in the product and integrated will equal to the Ez fields and the integration of Ez's field. And this integration is calculated in the problem A, so we know that it is orthogonal to each other for all if the transverse E field is both TM modes. And for both TE modes, we need to calculate it again. And because the ET is equal to the Z cross the gradient H, so we use some vector calculus identity to change this cross product to the dot product here. And because the Z dot gradient T is equal to 0, this is the identity because gradient T is in the transverse direction and our Z is longitudinal directions. So our ET's integrations is equal to the gradient H's integrations. And again, after we use the green theory, we now can use the TE's boundary condition to eliminate the first terms. And the second terms again, because it satisfies the wave equations, so we can change the Laplace operator to a gamma lambda square. And from the problem A, we know that the HZ field is orthogonal to each other. So for both T and modes, it is orthogonal too. And for one TE and one TM mode, the mixing case, and you can calculate from just plug in and use the vector identity. And the last step is the sometimes green theory. We call it Stokes theory here, and maybe in the applied math course. After we use the Stokes theory, we can find that because of the T mode boundary condition, your E field is vanished at the surface. At TM mode boundary condition, sorry. Your E field will vanish at the surface, so this integration is identically to 0. So if you are T mode times a TM mode, the integration is always 0, no matter your mu or lambda are the same or not. So for equation A.132, the H fields inner product and the integration of H fields inner product. And you can change the H field by the definition. H is equal to the Z cross ET, and change the product from the inner product, integration of H field inner product to integration of E fields inner product. And then use the equation A.131. You can find that it is basically the same, but just up to an impedance constant here. And the equation A.133 is the power flow relations. And again, we can change the H field to the E fields and use the equation A.131. You will find that the orthogonal relation is still holds, but there's another impedance constant in the denominator. And finally, from the previous calculation, the equation A.100 and the equation of A.134 is want us to show the appropriate normalization of the EZ field. And from the previous work and previous calculation, we know that for TM mode and TE modes, the integration is equal to, finally will equal to the EZ's integrations. And so if you want to if you want to normal and unit normalizations, we need to make our EZ fields is equal to these two constants. Okay. Okay, finish.